Think about being in a pitch black room. You know, you can't see a thing.
Right.
Then, click, the light flips on, and suddenly everything is just visible. It's almost unbelievable how this basic form of energy, light, just completely changes our perception.
It really is fundamental, isn't it?
Yeah.
And that instant shift, darkness to light, it just underscores its power. So in this deep dive, we're going to really try and illuminate light itself.
Illuminate light. I like that.
Yeah, we're sort of on a mission to explore where it comes from, how it interacts with, well, everything around us, its unique way of traveling, and those fascinating things it creates, like, shadows and eclipses. Our journey, it's guided by some core educational materials that lay out the basics.
Exactly. And look, getting a handle on light isn't just some abstract science lesson.
No, not at all.
It's fundamental to how you experience the world. Like right now, consider the screen you might be looking at, or just the colors you see every day. It all boils down to light and how it behaves. Okay, so let's dive in. What is light at its heart?
Essentially, light is a form of energy. More specifically, it's the kind of energy that triggers our sense of sight.
Right.
Now, here's a key point to kind of wrap your head around.
Yeah.
We can't directly see light itself. We perceive its effects, when it bounces off objects and then hits our eyes. It's a bit like wind. You can't see the wind, right?
Yeah.
But you see the trees moving.
That's a really helpful way to think about it. And one of the really intriguing things about light is how it travels, isn't it? Like, unlike sound needs air or water or something.
Exactly.
But light can just zip through empty space.
Precisely. Light doesn't require a medium. It doesn't need anything to travel through. That's how sunlight gets here. Across that huge vacuum between the sun and Earth. It makes life possible. It's a crucial difference from, say, sound waves. And what's particularly interesting is the way it makes this journey.
You mean how it always goes in straight lines? Like a flashlight beam cutting through the dark?
Yep.
You can't really shine it around a corner?
Exactly. That's known as the rectilinear propagation of light. Bit of a mouthful, but
yeah.
it just means light travels in straight lines. We often draw them as rays.
Okay.
And when you get a whole bunch of these rays going in the same direction, that's a beam of light.
Right, a beam.
And these beams can vary. You can have parallel beams, like light from a really distant star. The rays are basically side by side. Then there are divergent beams where the rays spread out, like from a torch.
Makes sense.
And convergent beams where rays come together at a point. Think magnifying glass, focusing sunlight.
Right, like using a magnifying glass. Though, yeah, be careful doing that.
Definitely.
And this straight line thing, it's not just theory, is it? We can see it with some pretty simple demos.
We absolutely can. Think about trying to look at a light through a straight tube, like a paper towel roll.
Yeah.
You can see the light, but then bend the tube.
Light's gone.
Exactly. The light can't follow the curve. Or another one is lining up holes in pieces of cardboard. Look through the holes at a candle.
You see the flame.
Yep. But nudge one card slightly out of line.
Blocked it.
Blocked again. Light doesn't just bend around corners normally.
Okay, so light travels straight. Now, where does it actually come from? We've mentioned the sun, but there must be other sources.
Absolutely. We can basically split light sources into two main types, natural and artificial, or human-made.
Okay, natural and artificial. That makes sense. So natural is like the sun, stars, things that just make their own light.
Precisely. And the sun is, well, undeniably the most critical natural source for us here on Earth. It's incredibly far away, about 150 million kilometers.
Wow.
But the light it pumps out is powerful enough to light our day, drive weather, grow plants, everything.
Yeah.
Other stars, also natural sources. Some are way brighter than our sun, actually, but they're so immensely distant, they just look like tiny specks.
Twinkling dots?
Right. But there's another fascinating type of natural light source, too. One involving living things.
Oh, you mean like things that glow? Like fireflies?
Exactly like fireflies. It's called bioluminescence, the production and emission of light by living organisms.
That's amazing.
Fireflies, glowworms, some sources mention jugnu, even some fungi and deep-sea fish. This light isn't from heat, though. It's a chemical reaction inside the organism.
Chemistry making light.
Yeah, a direct conversion of chemical energy into light energy.
Yeah.
It's really efficient, produces very little heat. So yeah, these are definitely natural light sources. It's used for all sorts of things, attracting mates, luring prey.
Incredible. Nature's own little LED lights. But, okay, obviously not everything we see makes its own light. Like the moon, it's super bright sometimes, but it's not a star.
Exactly right. Objects that don't generate their own light are called non-luminous bodies.
Non-luminous, okay.
We see them because they reflect light from luminous sources. The moon is the perfect example. Our materials even state it clearly. The moon is a non-luminous body. The light we see from it. That's just sunlight bouncing off its surface and traveling to our eyes. It's like a huge dusty mirror in space.
So it's borrowing sunlight.
Got it. Okay, so we have light sources, natural and artificial, and light travels straight. But what happens when light, hits different stuff, different materials? Does it always just go through?
Oh, definitely not. How light interacts with a material is key. It determines if we see through it, if it looks blurry, or if we can't see through it at all.
Right.
We classify materials based on this interaction. First, there's the idea of an optical medium that basically any substance light can travel through, even partially.
Okay, a medium.
These can be homogeneous, meaning they're uniform all the way through, like pure glass or still water.
Smooth.
Or heterogeneous, where the density varies. Think air on a really hot road, that shimmering effect. Or fog.
Ah, right. Heat haze. Got it.
Yeah.
So within these mediums, materials act differently. Transparent ones are the see-through ones.
Yes. Transparent materials let light pass straight through with very little scattering. You see clearly. Glass, water, clear plastic.
Like windows, glasses. Exactly. Used for windows, spectacles, lenses and microscopes, telescopes. All rely on transparency. Though even environmental factors can affect it slightly, like high humidity making the air seem less clear.
Yeah, you notice that. Okay, so transparent is clear. Then there's translucent. That's like in the middle.
Precisely. Translucent materials let some light through, but they scatter it.
Scatter it.
Yeah, so the light gets jumbled up as it passes through. You get a blurry or fuzzy view of what's behind. Think tracing paper, waxed paper, frosted glass.
Ah, like bathroom windows sometimes.
Exactly. Used when you want light, but also privacy. You see light, but not sharp details.
Okay, so transparent, clear, translucent, blurry light, which leaves opaque, the total blockers.
That's it. Opaque materials don't let any significant light cast through. Wood, metal, thick cardboard, stone. When light hits an opaque object, it's either absorbed, turns into heat usually, or it's reflected off the surface. That reflection is how we see the object itself if it's lit up.
So opaque is for blocking light completely.
Right. And there's simple ways to test this. Activity 3 in our materials suggests shining light on things like plywood, glass, foil.
Just to see what happens.
Yeah. See clearly. Transparent, no light. Opaque, some light, but fuzzy. Translucent. Our source even has a little table for results.
Article.
And there are questions asking you to classify things like a glass strip, transparent, paper, translucent usually, milk, translucent, a book, opaque, kerosene oil, transparent. It helps lock in the ideas.
Makes sense. It really comes down to the material's internal structure, doesn't it? Okay, so light travels straight, interacts with materials. Now let's talk about the pinhole camera. That sounds like a really neat way to see the straight line thing in action.
It is. It's wonderfully simple, but perfectly shows that rectilinear propagation principle.
How does it work? Could you, make one?
Oh, easily. You just need a box that's light tight. Cardboard works fine.
Okay.
Make a tiny, tiny hole, literally with a pin in the middle of one side. Then on the opposite side, inside the box, you put a screen. Thin wax paper, tracing paper is good.
A screen inside.
Yeah. And it helps to blacken the inside of the box, maybe with paint or paper, to stop stray light bouncing around and blurring things.
Okay, sealed box, pinhole, screen. Black, inside. What happens if you point the hole at something bright, like outside?
Well, light rays from the scene travel in their usual straight lines. They go through that tiny pinhole.
Okay.
Now think about it. Light from the top of, say, a tree travels straight through the hole and hits the bottom part of your screen inside.
Ah, because it's going straight, diagonally downwards through the hole.
Exactly. And light from the bottom of the tree travels straight through the hole and hits the top of the screen.
So everything's flipped.
Everything's flipped. Light from all the points in between does the same thing. So what you see projected onto that wax paper screen is a complete but upside down image of the scene outside.
Upside down. That's wild. What else is true about that image? Is it sharp?
Well, it's what we call a real image because the light rays actually meet on the screen. It's inverted, as we said, and usually it's smaller than the actual object.
Interesting. Does the size change? Like if the object is further away or the box is bigger?
Absolutely. Two things mainly affect the size. First, the distance from the pinhole to the screen inside the box. Make the distance longer, the image gets bigger.
Okay.
Second, the distance from the object outside to the pinhole. Move the object further away, the image gets smaller.
Ah, that makes sense.
There's even a formula for it. The magnification, how much bigger or smaller the image is, depends on those two distances. The ratio of image height to object height equals the ratio of image distance to object distance.
Wow, okay.
Maths. But it shows the relationship clearly. It's amazing such a simple box can do all that. And it's not new, right? This sounds old.
Very old. Our source mentions the principle was known way back in the 11th century in the Arab world. They called it camera obscura.
Camera obscura.
Dark room.
Literally dark room, yes.
Yeah.
They even used it to safely watch solar eclipses.
Yeah.
Later on, Leonardo da Vinci described it and apparently called it the pinhole camera. So yeah, centuries old.
Incredible. But compared to, the camera on your phone, what are the pros and cons? Is there any advantage?
Well, the big advantage is its simplicity. No focusing needed. And because there's no lens, you don't get lens distortions like weird color fringes or blurriness at the edges.
Okay. Disadvantages?
The image is usually pretty faint. Only a tiny bit of light gets through that hole, so it often lacks detail. And it's formed right there on the screen, not easy to save permanently. Plus, because it's faint, you need long exposure, so it's no good for moving objects. They'd just be a blur.
Right. Great for understanding light, maybe not for sports photography.
Exactly.
But hang on, the sources mention natural pinhole cameras. What's that about?
It's really cool, actually. Ever noticed on a sunny day under a leafy tree, the patches of sunlight on the ground?
Yeah, dappled light.
Look closely sometime. Often, those patches are roughly circular, even if the gaps between the leaves are all jagged and irregular shapes.
Yeah, I think I've seen that.
Those little round patches, they're actually pinhole images of the sun. Each tiny gap between the leaves acts like a natural pinhole. Light travels straight through, projecting little front images onto the ground.
No way. So the gaps between leaves are acting like thousands of tiny pinhole cameras.
Effectively, yes. Nature doing physics.
That's brilliant. Okay, so light travels straight, interacts differently with stuff, makes upside-down images through small holes. Now, let's talk about what happens when something blocks that straight path. Shadows.
Shadows, yeah. A direct result of light traveling straight and hitting opaque objects. An opaque object gets between a light source and a surface. It blocks the light rays. The area behind the object where light can't reach, that's the shadow, a dark patch.
So you need three things.
Exactly. Light source, opaque object, and a screen or surface for the shadow to fall on. Without the surface, there's still a region of blocked light, but you don't see the shadow.
Right, and shadows aren't always just black blobs, are they? Sometimes there's a darker bit and a fuzzier bit.
You're right. That depends on the light source. Yeah. If you have a tiny point source of light, the shadow is usually sharp and uniformly dark. That's called the umbra.
Umbra, okay.
But most light sources, we encounter a light bulb. The sun, they're bigger. They're extended sources.
Right.
So with an extended source, the shadow often has two parts. There's still the umbra, the really dark central part where all direct light is blocked.
Total shadow.
Total shadow. But around it, there's often a lighter, fuzzier region called the penumbra.
Penumbra.
In the penumbra, some of the light from the source is blocked, but not all of it. If you were standing in the penumbra, you could see part of the light source, but not the whole thing.
Okay, so umbra is total blockage, penumbra is partial blockage. And the type of shadow must depend on the object too? Opaque, translucent?
Absolutely. Opaque objects, they block light well, so they cast dark, clear shadows.
Makes sense.
Translucent objects, they let some light through, remember. So their shadows are much fainter, weaker, sometimes hard to see. And transparent objects, ideally, letting all light through. They shouldn't cast any shadow at all.
Right. And our sources mention Activity 7 shining a torch on someone outside. They don't seem to have a shadow until they stand near a wall.
Exactly. Perfect demo that you need that surface, that screen, for the shadow to be visible.
And shadows look like the object. Mostly.
Mostly, yeah.
Yeah.
The outline is often similar, but the shape and size can change a lot depending on the angle of the light. Think about your own shadow tepid skills. Activity 8 has you move a torch around a book. You see the shadow stretch, shrink, change shape. We can often guess an object from its shadow, but sometimes it can be really distorted.
Like our own shadows during the day, they start off really long in the morning, then get tiny at lunchtime, then long again in the evening. Why is that?
That's all down to the sun's position in the sky. Morning and evening, the sun is low, near the horizon.
Right.
So the light hits us at a low angle, stretching the shadow out behind us. Long shadows. Around noon, the sun is high up, almost directly overhead. The light comes down more vertically. So your shadow is much shorter, almost just beneath your feet.
Clever. It's just geometry, really. Okay, shadows, blocking light. Now for some really big shadows. Eclipses. Solar and lunar.
Yes. Eclipses are just enormous shadow plays in space. A solar eclipse. That happens when the moon passes directly between the sun and the earth.
Moon in the middle?
Moon in the middle. It casts its shadow Umbra and Penumbra onto a part of the earth if you're in that shadow path.
You see the sun get blocked.
Exactly. Partially or even totally if you're in the Umbra. Our materials have a simple diagram showing that alignment.
Okay, so solar eclipse is the moon's shadow on Earth. Lunar eclipse must be the other way around.
It is. A lunar eclipse happens when the Earth passes directly between the sun and the moon.
Earth in the middle.
Earth in the middle. So
yeah.
The Earth casts its shadow onto the moon. As the full moon moves into Earth's umbra, it gets dark. It can even look reddish sometimes because of sunlight filtering through Earth's atmosphere. Again, there's a diagram showing this.
So the moon passes through Earth's shadow. It's all about who's casting the shadow on whom.
Right. Okay, changing gears slightly. Our sources mention light intensity, measuring brightness.
Yeah.
How do we do that?
Right. Brightness. It's measured by luminous intensity. Historically, unit was candle power.
Candle power. Like how many candles bright?
Pretty much. It compared the light source's brightness to that of a standard candle. So you might say a lamp was, I don't know, 20 candle power.
Sounds a bit old-fashioned. What do we use now?
It is a bit dated. The modern standard unit is the lumen. Well, technically luminous intensity is in candelas, but the total amount of light pouring out in all directions, the luminous flux, that's measured in lumens.
Lumens. Okay, I've seen that on light bulb packages.
Exactly. Our sources give a conversion, something like 1 candle power equals 1256 lumens, roughly, for total output. So lumen is the key measure of overall brightness today.
Lumen. Got it. And one last thing from the sources. Hot versus cold light sources. What's the difference there? It's pretty straightforward, actually. It's about whether the light comes with a lot of heat. Hot sources produce light and heat together. Like an old-style incandescent light bulb with the glowing wire filament gets really hot, right?
Yeah, definitely.
Or a burning candle flame or an incense stick. They glow because they're hot. That's incandescence.
Okay, so hot means light plus significant heat. So cold sources.
Cold sources emit light with very little heat produced at the same time.
Examples.
Our firefly friend, again bioluminescence, is a cold light process. Or a fluorescent tube light, or an LED. You can usually touch a lit fluorescent tube and it's warm, maybe, but not burning hot like an incandescent bulb.
Right, much cooler.
They use different processes. Fluorescents, LEDs use semiconductors that convert energy to light more directly without needing that intense heat.
That makes a clear distinction. It's about the heat byproduct.
Okay, good.
Wow, we have really gone deep into light today, from what it is to how it travels to shadows and eclipses.
We certainly have. Just to quickly recap the big ideas. Light is energy, travels straight. Sources are natural sun, stars, amazing bioluminescence, and artificial. It interacts with materials. Transparent lets it through clearly. Translucent scatters it. Opaque blocks it.
Got it.
The pinhole camera shows that straight lines travel beautifully, creating inverted images. And shadows, umbra and penumbra, happen when opaque objects block light, leading even to eclipses on a grand scale. It's
really quite amazing how these basic ideas about light explain so much of what we see every day. So for you listening, maybe as you go about your day, just, notice the light, notice the shadows.
Yeah.
Think about why the window is clear but the frosted glass isn't. Maybe look for those natural pinhole effects under trees.
Definitely. And that leads us to a final thought, something to mull over. We've spent all this time establishing that light travels in straight lines, right?
Right. Rectilinear propagation.
So, how do rainbows happen? Where sunlight hits raindrops and suddenly you get this beautiful arc of colors. Light seems to bend and split apart. How does that fit with light always traveling in straight lines?
That's a really good question. How do rainbows fit in?
Something to think about. This shows there's always more complexity, more to understand, even with something as fundamental as light.